Good afternoon, everyone. On the behalf of Jogananda College of Engineering and Technology, I, Rohit Gupta, welcome all the people joining us. I convey my regards to the expert of the session, Dr. SANDEEP ARYA, who is an assistant professor in the Department of Physics, University of JAMMU. Dr. SANDEEP ARYA is an expert in synthesis of nanowires and their characterization for sensing and electronic application. He has more than 60 publications in the various international journals. He has membership in professional bodies like PLOS1, ECS Journal of Solid State and Technology. He is an editor of the National Journal of Nanoelectronics and Materials. He has completed research project electrochemical synthesis of nanowires and their physiochemical parametric evaluations for sensor applications, funded by Science and Engineering Research Board. He has also completed research project design of low power integrated antenna for Bluetooth applications, funded by University Grant Commission. Thank you so much, sir, for accepting our invitation and coming over for the extension lecture. Thank you, sir. Now I request Director Ycet, Professor A.K. Srivastava, to say a few words. Over to you, sir.
Okay. Rohit, am I audible?
Yes, sir.
Okay, thank you. Thank you very much.
Thank you, sir.
Respected Dr. SANDEEP ARYA from University of Jammu, Head of the Department of Applied Science, Dr. Rakesh Verma, faculty members of Applied Science Department, and my dear students. A very good afternoon to all of you.
Good afternoon, sir.
First of all, let me congratulate Applied Sciences Department for organizing a webinar on a very important topic like semiconductor and their innovation in technology. In fact, under the IIC cell, we have been conducting the webinars, organizing such kind of the programs, and the other departments like civil engineering, mechanical, electrical, and computer science, they have already arranged many, you can say, webinars under the IIC. So I'm very happy that the Applied Sciences Department has organized this kind of the webinar, and he has invited Dr. SANDEEP ARYA, who is assistant professor in Department of Physics, University of Jammu. He will be delivering a lecture. But the most important thing, let me tell to the students that the topic which has been selected is very, very interesting, like semiconductors and their innovation in technology. In fact, I would like to say a few things about the semiconductor devices, that as all of you will be knowing that the semiconductor manufacturing devices is basically a very costly affair. And if we talk about the, microprocessors, microcomputers and all, which are using the semiconductors, so it is very, very costly. And here I would like to mention, in fact, one paper which was being written by C. Makatsoris from Imperial College of London. He wrote a paper sometime in 90s, probably it was 93, 94, and he did mention about the semiconductor manufacturing. And he, in his paper, he wrote that, say, for example, design is taking place at a place called Rich. Wafer fabrication is taking place at California, and burning process is taking place at Germany. Assembly is taking place at Korea, and testing process is being done at Manila, and finally the customer are, let us say, at Sydney. So you can just imagine that the manufacturing of semiconductor devices, which requires a lot of sophisticated, R&D labs and things like that. So it is very difficult for a single company to have the complete infrastructure. And then he gave the idea of virtual enterprise, that why not all these companies, they join together and come out with the product. And to be very honest, that from this paper, my research was started, and my whole PhD was related to this implementation of the virtual enterprise, So I hope that the talk by Dr. Sandeep Arya on the semiconductor and their innovation in technology is going to be very, very fruitful for our students, and our students will get a lot of advantage. I wish all the best to Dr. Sandeep Arya for his. Thank you very much. Thank you.
Thank you so much, sir. Without further delay, I request Dr. Sandeep Arya, sir, to address the students and cast the light of his knowledge upon them. Over to you, sir. Sunil.
So I hope my slides are visible. Is it visible?
Yes, sir.
Okay. So first of all, I would like to thank the organizers who have given me this opportunity to interact with the students. And thank you, Rohit, for your lovely introduction.
Thank you, sir.
So as actually it is today's webinar, it is all started by the worthy director of your institute. And if I am right, he's person from electronics background. And it was, yes, he's right that actually when these semiconductors, it was started, it was not at one place.
Dr. Sandeep Arya,
Yes,
sorry
yes.
to interrupt you. My background is not electronics. My background is in fact computer science.
Okay.
And it is artificial intelligence. So in fact, I implemented the whole model which I was talking about, the virtual enterprise, using the software agents. So the whole thing was simulated using the software agents. So it's a computer science. So yeah, but the topic was definitely from electronics, you can say. So thank you.
Okay. So nowadays it is actually, the research is more or less, it is interdisciplinary, so it hardly affects, but it was very nice from you that you are from the background of computers, but still you have some knowledge about semiconductors. Nowadays I have seen the students who actually thinks that semiconductor is not of our area, especially the students from stream other than electronics. So let me start with our today's lecture, which is about the introduction and application of semiconductors. So this presentation, it is very, very basic, as I came to know from Rohit, that the students who are actually listening to this lecture, they are from, I think, first or second semester students?
Yes, sir.
Okay. So first of all, we should know about semiconductors. What are semiconductors? These are the materials whose electronic properties, they are in between the metals and insulators. So that means if we talk about the conductivity of semiconductors, it lies in between metals and insulators. The conductivity of semiconductors, as I have written here, it ranges between 10⁻⁻⁴ to 10⁻+4 Simon per meter. So, due to some interesting characteristics of these semiconductors, they are have vast applications in electronics and electrical device formations. So, the known best known semiconductor elements, they are silicon and germanium. As you can read it, silicon and germanium are elemental semiconductors. And they have 4 valence electrons, which are distributed among the outermost s and p orbitals. When we talk about semiconductors, semiconductors are of 2 types. One is intrinsic semiconductor and another is extrinsic semiconductor. Intrinsic semiconductors are pure semiconductors. That means the semiconductors in which there is no impurity. Whereas extrinsic semiconductors, they have some impurity which are doped into it so that their characteristics modifies. So this is, you can see in this slide about intrinsic semiconductor, a semiconductor which does not have any kind of impurity. And these semiconductors, intrinsic semiconductors, they behave as insulator at absolute temperature. Absolute temperature means at 0 Kelvin, and it can act as conductor as well at higher temperatures. So these are the characteristics of intrinsic semiconductors. They can act as insulator as well as conductor depending upon the temperature at which it is operational. So silicon and germanium both belongs to 4th group of periodic table, and they are very well researched elements as far as semiconductors are concerned, and both are the examples of intrinsic semiconductors. And you can see on your right hand side a diagram of this covalent bond formation, in which you can see that the at their outermost shell there are only 4 atoms present. So you can see this, the energy band diagram of intrinsic semiconductor. And when we talk about intrinsic, this energy band diagram, what we have actually, we want to determine about the energy gap between valence band and conduction band. I already told you that the characteristics of semiconductors, they lies between insulators and metals. In metals, what happens if we see the energy band diagram of metals, the valence band as well as conduction band, they both are very much nearer to each other, and sometimes they overlap. So that means the energy band gap between, that means the distance between the top of valence band and the bottom of the conduction band for metals is very, very less. And if we talk about insulators, what happens in insulators, this distance is very big distance. That means the electrons from the valence band cannot go into the conduction band, okay, because they don't have that much of energy. But whereas if we talk about intrinsic semiconductor, you can see from this valence band diagram, this energy band diagram, that we have valence band, we have conduction band, and in between we have Fermi energy level. And this is the level if electron will be able to cross this Fermi energy level, certainly it will go into the conduction band. And if it is intrinsic semiconductor, this Fermi level, it lies exactly at the middle of the bottom of conduction band and the top of valence band. And you can see here in right hand side, you can see that how much energy, kinetic energy, this electron which is present in the conduction band is E minus EC. Okay, that means total energy minus energy of this electron which is present in conduction band. Whereas since at the initial stage our electrons was in this valence band, and when it moves into the conduction band due to some external energy or due to some any kind of energy, so a void is created, and which is nothing. We assume it as a hole, and you can see the kinetic energy of hole. It is written here as EV minus E. So you have seen this the energy band diagram of intrinsic semiconductor. You came to know about intrinsic semiconductor. I am very sure that you know a little bit about intrinsic semiconductor, but what about the carrier concentration in intrinsic semiconductor? So if we want to know a carrier concentration of intrinsic semiconductor, so we should know these things, that when a suitable form of energy is supplied to a semiconductor, that means when this semiconductor has certain kind of energy, if we provide that kind of energy, then what will happen? As I already told you, that there is transition of electrons from valence band to conduction band. Okay, but a free electron in conduction band and simultaneously free hole in valence band, when they are formed, then this is known as generation of electron hole pair, because hole is created only when there is transition of electron from valence band to conduction band, and due to void created in valence band, that means empty space created in valence band, that is actually assumed as hole, and that means an electron hole pair is generated. And in intrinsic semiconductor, number of conduction electrons will be equal to number of vacant sites or holes in valence band. Okay, so in this diagram you can see jitne electrons, that means the number of electrons, if there are n number of electrons in valence band, and if they crosses this Fermi level and goes into the conduction band, so there will be holes. How many holes? Equivalent to the number of electrons which gets transited from valence band to conduction band. So that is what it is written, that in intrinsic semiconductor, number of conduction electrons will be equal to number of holes in valence band. So in intrinsic semiconductor, n is equal to p. That is why you have seen that why n is equal to p in intrinsic semiconductor, and this n is equal to p, it is assumed to be equal to ni, and ni is nothing but this is known as intrinsic carrier concentration. That means how many carriers we have. That means what are the concentration of carriers in intrinsic semiconductors. Okay, so this was a little bit concept about the intrinsic carrier concentration in semiconductors. And in intrinsic semiconductors, the Fermi energy level is located in middle of forbidden energy gap or forbidden band. One more thing you should know. Again, I am sure that you know this thing, that at 0 Kelvin, as we know that it acts as insulator. That means what will happen? We have electrons only in valence band, and our conduction band will be empty at that time. Okay, and when we give certain energy to it, then only electrons can move from valence band to the conduction band. So let me move ahead about, okay, and try to know about the extrinsic semiconductors. So as I already told you, and you know that extrinsic semiconductors can be formed when we dope a kind of impurity into it. So extrinsic semiconductors are those in which impurities of large quantity are present. Usually we have two types of impurities that we can dope into it. That means to make extrinsic semiconductor, we will dope either third group elements or fifth group elements in an intrinsic semiconductor. And based on these impurities present, whether it is impurities from third group or impurities from fifth group, there are two categories or two types of extrinsic semiconductors. One is N-type semiconductor and another is P-type semiconductor. N-type semiconductor, you can see. If we want to get N-type semiconductor, what we have to do? We have to dope the element, or we can say the impurity, which is from fifth group of periodic table. So the intrinsic semiconductors doped with pentavalent impurities, such as phosphor, arsenic, etc., they are called N-type semiconductors. So the energy level of fifth electron is called donor level. So they are known as donor levels. So the donor level is close to the bottom of conduction band, and most of the donor level electrons are excited into the conduction band at room temperature and become majority charge carriers. Hence, in N-type semiconductors, electrons are majority carriers and holes are minority carriers. You can see a diagram given here in the right hand side. See, in silicon, in their outermost shell, we have 4 electrons. But if we are doping it with any pentavalent impurity, then you can see that in its outermost shell we have 5 electrons, and so 5 plus 4 is 9. You can see 1, 2, 3, 4, 5, 6, 7, 8, and this one is extra electron. Okay, so because we know that if we want to stabilize the element, so what we require in their outermost shell, there should not be more than 8 electrons. Because if it is 2 or 8 or 18, as you already know this thing, that only then our element will be stable or material will be stable, but it has 1 extra electron. Okay, that is why you have seen this, that this is known as donor, because it has extra atom and he has to give it to another. So that is why it is known as a donor electron. So the energy level of fifth electron is called donor level. That is what it is written. And the donor level is close to the bottom of conduction band. Yes, it is true. And you can see this energy band diagram. Okay, you can see this donor level of N-type semiconductors. And we have valence band, we have conduction band. And this is the energy gap, forbidden energy gap between the top of valence band and bottom of conduction band. And this is our donor levels. So this donor level, you can see as it is written here, okay, is close to the bottom of conduction band. So that is why you can see that it is far away from the valence band. It is close to the bottom of conduction band. Now, what is the carrier concentration in N-type semiconductor? Let us suppose that we have donor concentration designated as ND. Okay, why this ND means this subscript D means donor, and this is N-type semiconductor. So we can write it as ND. So ND is the donor concentration. That means number of donor atoms per unit volume of the material, and let ED is the donor energy level. So we have 2 things here: ND, which is the donor concentration, and ED, which is donor energy level. So at very low temperatures, all donor levels are filled with electrons. Okay, and with increase in temperature, as we increase the temperature, more and more donor atoms it will get ionized, and the density of electrons in the conduction band increases. So more and more, because if temperature increases, that means it gets some external actuation, due to which these donor electrons they will transit into conduction band. And at 0 Kelvin, Fermi level lies exactly at middle of this donor level and the bottom of the conduction level. Okay, so it's Fermi level at 0 Kelvin temperature. It is exactly at the middle of this. So that is why sum of these 2 energy levels, that means ED is the donor energy level, and EC is the bottom of the conduction band upon 2. Okay, so this is EC, this is ED, and its Fermi level will lie in between, in middle of these two. So in short, we can say that in N-type semiconductor, the Fermi level will lie close to the conduction band. In intrinsic semiconductor, Fermi level was lying in the middle of these two. That means in the middle of this energy gap. Whereas in N-type semiconductor, Fermi level lies close to the conduction band. Let me move forward and we'll try to know about P-type semiconductors. And if we want to convert our intrinsic semiconductor into P-type semiconductor, what we have to do, again, we have to do certain kind of impurity into it. And it is known that if we do trivalent impurity, that means elements from third group of periodic table, like elements like aluminum, gallium, indium, etc., in which we have 3 electrons in their outermost shell, then a P-type semiconductor can be formed. So it is written here, when a trivalent element such as aluminum, gallium, or indium have 3 electrons in their outermost orbit, all the 3 electrons of indium are engaged in covalent bonding with the 3 neighboring silicon atoms. And here it is taken an example of indium, any of these impurities. So indium needs 1 more electron to complete its bonding. So again, if we want to make it stable, what we have, how many electrons we require in our outermost shell? 8. And you can see we have shared one electron from each silicon, and his own outermost shell electrons are 3. So you can see these 4 plus 3 becomes 7, and there is short of 1 electron. So this electron may be supplied by silicon, thereby creating a vacant electron site or hole in semiconductor atom. So if silicon will share this space to make this stable, but this silicon will become short of 1 electron. And if electron will move from this side to this side, and we came to know similar to our energy band diagram, as I have discussed earlier, that when electron leaves its original site and transit into another site, what happens? A void, which is also known as hole, is created. Okay, so these type of trivalent impurities are called acceptor impurities, because this has to accept 1 more electron, and the semiconductors dopes the acceptor impurities are called P-type. So again, we will try to know about its energy band diagram. So here you can see, here our acceptor level is close to the valence band, top of the valence band. Again, our energy band gap will remain same. That means it will from the top of valence band to the bottom of conduction band. But these acceptor levels, these holes, they all will be close to the top of valence band. Even at relatively low temperatures, these acceptor atoms get ionized, taking electrons from valence band and thus giving rise to holes in valence band for conduction. And due to ionization of acceptor atoms, only holes and no electrons are created. Thus, holes are more in number than electrons, and holes are majority charge carriers, and electrons are minority carriers in P-type semiconductor. So these few lines and these few sentences, they make us to understand that how P-type semiconductors has holes as majority charge carriers in it and electrons as minority charge carriers in it. Whereas in N-type semiconductors, electrons are majority charge carriers and holes are minority carriers. So till now we came to know about the type of semiconductors, like P-type semiconductor, N-type semiconductor. But these types are according to the the impurity present in it, impurity doped in it. Okay. Originally, there were two types of semiconductors, intrinsic semiconductor and extrinsic semiconductor. Okay. But we can also classify semiconductors as direct band gap and indirect band gap semiconductors. So let me read this. In few crystals like gallium arsenide. So gallium arsenide is again well-known semiconductor. The maximum of valence band occurs at the same value of K as the minimum of conduction band as shown. I will tell you later on. This is called direct band gap semiconductor. And in few semiconductors like silicon, the maximum of the valence band does not always occur at the same K value as the minimum of the conduction band as shown in figure. This we call indirect band gap semiconductor. In direct band gap semiconductor, the direction of motion of electrons during transition across the energy gap remains changed. This is very, very important. In direct band gap semiconductors, direction of motion of an electron during transition across energy gap remains unchanged. Hence, the efficiency of transition of charge carriers across band gap is more in direct band gap semiconductor than in indirect band gap semiconductor. So I don't know you came to know, you are able to understand these lines or not, but I am sure that from these band gap diagram, you will be able to know the classification of direct band gap semiconductors and indirect band gap semiconductors. In indirect band gap semiconductor, examples of indirect band gap semiconductors are silicon and germanium. Okay, this is indirect band gap semiconductor. We have examples of silicon and germanium. What happens here? You can see this is momentum on x-axis and this is energy on y-axis. Momentum is designated by K, which is written here that the value of K. What is K? You may actually was confused at that time, but let me tell you, this is momentum, this is energy. Now, whenever you can see what happens, this is our, now this is the top of valence band, and this is the bottom of conduction band. That is why you can see here it is written that this is energy band gap. So actually here the electrons which are going to transit from valence band to conduction band, it is actually indirect transition. It is not going directly into the conduction band. You can see because there is shift in momentum. Whereas here in direct band gap semiconductor, you can see this is the bottom of conduction band and this is the top of valence band. And you can see whenever due to excitation, when electron will transit from valence band to conduction band, there is a direct transition. There is no change, no shift in momentum. Okay, this is the energy band diagram, and you can see whenever there is no shift in momentum, that kind of semiconductors are known as direct band gap semiconductors, and whenever there is shift in momentum, okay, that kind of semiconductors are known as indirect band gap semiconductors. Okay, well-known example of direct band semiconductor is gallium arsenide. That is right in my previous slide. It is gallium arsenide written. And the examples of indirect band gap semiconductors are silicon and germanium. And ultimately, what happens in direct band gaps? If we have direct band gap semiconductor, the energy released in the energy which is released while transition of electrons and holes, the energy is released in the form of light. That is why gallium arsenide is a kind of material which has its applications to fabricate LEDs, light emitting diodes. Whereas here, whatever the energy is released, it is released in the form of heat. Okay. So this was one aspect which covers semiconductors and their classification. Now we know that we can form a junction by fusing together two different extrinsic semiconductors. So we can form p-n junction. That means when we are able to fuse p-type semiconductor with n-type semiconductor, so p-n junction will form. So a p-n junction is an interface or boundary between two semiconductor material types, and these two semiconductor material types both are extrinsic one, which is p-type and n-type. The p side or the positive side of the semiconductor has excess of holes. You can see if this is p-type material and this is n-type material, this p-type will have excess of holes and this n-type will have excess of free electrons. And this is the symbol of p-n junction type. And due to minority, okay, now this is our unbiased p-n junction. That means we have not biased it. Biased means that we have not applied any external power supply to it. Now, when we will not apply any external power supply with this, what will happen? When we fuse together p-type material with n-type material, there will be flow of charge carriers, random flow of charge carriers, and ultimately they will settle down by creating a boundary of electrons here and the boundary of holes here, and both will not allow any further movement of or diffusion of electrons into n-type side, n side, and diffusion of electrons into p side, thus creating a region, okay, depletion region. It is known as depletion. So you can see this band diagram. There are a number of figures given. You can see that to form a p-n junction, what is required? A p-type semiconductor and n-type semiconductor. When both p-type and n side are joined together, so this is p side and this is n side, they are joined together, there will be a random flow of these charge carriers. Because n has electrons as majority charge carriers, p has holes as majority charge carriers. These holes will try to penetrate inside the n side, and these electrons will try to penetrate into p side. And you can see ultimately after some time they will settle down and they will create a region known as depletion region. And you can see at thermal equilibrium, this will be the energy band diagram when both p and n side are joined together, or we can say that when a junction is formed in between, a p-n junction is created. When p-n junction is created, so this band diagram will we can see. So you can see this is the Fermi level. Okay, in p-type semiconductor, this Fermi level, it is nearer to the top of valence band, and n side you can see that this Fermi level is close to the bottom of the conduction band. So this is how actually we can show it in a schematic way. Okay, and there are two types of currents which is responsible for the conduction of diode. These two currents are drift current and diffusion current. Okay, and this was the diagram which shows that energy band diagram of p-type material and n-type material. So these two when comes together, so we can represent it like this. So you can see that whenever we want to know about the electrostatic potential of such p-n junction, so it can be represented by Poisson's equation. So which says that it is well-known equation which says that d2 xi by dx square, it will be equal to minus dv by dx or rho s minus rho s by epsilon s. And If we substitute the value of rho s, it will ultimately comes to be minus q by epsilon s and d minus na plus p minus n. That means these both are charge carriers, and these are the concentration of p and n. So all donors and receptors, they are ionized. So in regions far away from the metallurgical junction, charge neutrality is maintained and space charge density is 0. That means this d2 xi by dx square will be 0. That ultimately means that nd minus na plus p minus n will be equal to 0. Okay. So if we shift it, it comes out to be nd plus p will be equal to na plus n. And the total electrostatic potential between p side and n side under neutral regions at thermal equilibrium, it is known as built-in potential. That means the potential which is required to eliminate this depletion region, जिसकी वजह से हम depletion region को eliminate करें, खत्म कर दें, that the amount of potential which is required is known as built-in potential, and it is equal to xi n minus xi p, which is nothing but equal to kT by q natural log Na and d by Ni square, where Ni is the intrinsic carrier concentration. So again, from this diagram you can see this is actually how p and n junctions are formed, and you can see this diagram here. You can see this is Nd minus Na. Okay, so this actually gives us the space charge distribution. Okay, and this is charge density due to uncompensated impurity ion. So you can see the charge densities. This is for p side. Okay, and this is for this depletion region. This is our n side. This is n side, this is our p side, this is our depletion region, and nearer to p side, you can see the charge density here, and this is the charge density nearer to n side. So this is built-in potential. That means since this is the Fermi level, and whenever electrons will try to transit from valence band to the conduction band, they require this built-in potential. Then only, because this is the bottom of conduction band, this is the top of valence band. So to get into the conduction band, so this is the potential it is required. Now when we apply forward bias, that means when we apply positive supply to the p side of semiconductor with respect to n side, you can see that this due to potential, whenever this forward voltage it crosses this voltage, the conduction will start. That means now there will be flow of current from this device, through this device rather. Okay, and you can see this built-in potential, it will get increased when we will apply a reverse voltage. That means during reverse bias. During forward bias, what we require, we want to reduce and ultimately to eliminate the depletion region. But if we apply reverse voltage, this depletion, the width of depletion region will also increase up to a certain extent. And this is well known, you know this thing, but I doubt that all of you may know this thing. That is why actually I tried to actually put these slides for this presentation. So this is the IV characteristics of PN junction diode. Obviously, this is for indirect semiconductor. PN junction diode made from indirect semiconductor. You can see this is the forward conduction, and this is knee voltage jisko aap bolte ho. That is actually the built-in potential. And whenever it crosses built-in potential, current will start increasing with respect to small increase in voltage. And this is your forward conduction path. Whereas in reverse bias, you can see that because as you increase the reverse voltage, what happens? Your built-in potential also increases. That is why you will see that there will be no flow of current up to very large reverse voltage, and a time will come when there will be a breakdown, which is known as avalanche breakdown. When it happens, then current will start, a large current will start flowing. Okay, what is avalanche breakdown? That you know, because you have studied that in your 12th class also. So PN junction diode can be used as photodiode also, as the diode is sensitive to light when the configuration of the diode is reverse biased. Means to say that there are a number of devices where the reverse bias is also useful. Just like in your Xeno diode as voltage regulator, we use it in reverse bias. Similarly, the solar cell, we also use reverse bias. So when the diode is forward bias, it can be used for LED lighting applications. So as I already told you, if we are dealing with direct bandgap semiconductors like gallium arsenide, and for that kind of diodes, forward bias is actually the advantage, and we use their application in forward bias. And most of the applications of diode is while forward biasing. One of the well-known another application is a rectifier. Diode can be used as rectifiers also. And depending upon the type of diodes, there are a number of semiconductor diodes. Diodes can also be used as oscillators. And what are oscillators? Oscillators are those devices which are able to generate sinusoidal signals. So you can see the type of this, actually the pictorial representation of different kinds of diodes. You can see this is gun diode. They are all the semiconductor diodes actually. That is why actually I put this slide into it. So this is gun diode, this is laser diode, tunnel diode, and those who are dealing with these electronics, that means who are actually doing BTech in electronics, they ultimately in any of the semester you will be able to know about such devices also, microwave devices. And there are pin diode, we have LED, photodiode, this is for actor diode, Schottky diode, and this is our PN junction diode, CNR diode. And every diode has its own application. But one of the common significant application is that diode can act as a switch. During forward bias, it will act as closed switch, and during reverse bias, we can make it as open switch. So now we came to know about, I am not going into the what will be the behavior of these PN junction diodes during forward bias and what will happen in reverse bias, that you can understand. Also, one of the important aspect which you should study about these semiconductor diodes, it's about the Shockley's equation, current equation actually I can say. So you should know these things also. You should be able to derive it also. But since due to limitation of time, I am not going into that aspect. And now I can say that last few slides, they are about how we can identify the nature of semiconductor. Suppose you have a material, someone will tell you that it is actually, someone will say that this is actually a semiconductor, and you are very curious to know about what kind of semiconductor it is. Is it p-type semiconductor or n-type semiconductor? So that is what it is written here, that how we can identify the nature of semiconductor. That means nature means the the type of carriers it possesses. Okay, so we want to know about whether it is p-type or n-type. So there are two methods by which we can identify the nature of semiconductor. One is hard probe point test and another is Hall effect. This hard probe point test, this is the method by which we can determine the type of semiconductor, and it is very quick method and very simple method, but not the exact method. And this observation can be varied due to increase or decrease in temperature. So how we can know that it is n-type or p-type? So whatever the sample we have, if we will probe it with voltmeter or ammeter, and we will apply certain heat source, such as soldering iron or something like this. So due to heat, whatever the type of conductivity it possesses, that means whatever the charges it possesses, they will try to move away from the lead. and the heat from the probe creates increased number of carriers, and due to this you will see some variation in your current or voltage, and by which you can estimate that whether it is p-type semiconductor or n-type semiconductor. Here example is also given that if the heat source is placed on the positive lead of voltmeter attached with n side of semiconductor, attached to a semiconductor which you already know that it is n-type. So what will happen? A positive voltage will result. You can see the positive voltage. Okay, so a simple explanation is that the thermally excited magnetic free carriers move from the hot probe to the cold. So the mechanism of this motion in semiconductor is diffusion type, since the material is uniformly doped. So this was the one way by which we can estimate the nature of semiconductor or the type of extrinsic semiconductor, whether it is p-type or n-type. But there is another method which is very reliable method known as Hall effect. So there are a number of systems available in the market, which is Hall effect measurement system. There are certain practicals related to it also on graduation level, and in research also there are certain devices which are very, very expensive devices to know about the conductivity of semiconductor. So such devices are known as Hall measurement system, Hall effect measurement system. So this Hall effect was discovered in 1879 by Edwin Herbert Hall, and he was actually doing his PhD from Johns Hopkins University, US, and at that time he was able to discover it. So actually, what is Hall effect? Hall effect is the effect which is seen in a semiconductor when we place it under a magnetic field. So when a magnetic field is applied perpendicular to a current carrying conductor or semiconductor, a voltage will develop. Okay, and this voltage will develop in a direction perpendicular to both current and magnetic field. And this phenomena is known as Hall effect, and whatever the voltage will be developed, that is known as Hall voltage. Okay, so that means here all the three things like voltage, magnetic field, and current, they all are mutually perpendicular to each other. So let us consider a thin rectangular slab carrying current I in x direction. If we consider any slab, that means a semiconductor in which current is flowing in x direction, and if we place a magnetic field designated by B in y direction, then the potential difference which will develop, that is known as Hall voltage, it will be perpendicular to the z direction. So you can see this. Okay, so you can see if current is flowing in x direction, if we are representing our current in x direction, magnetic field in B direction, so our voltage, it will be in z direction. Okay, and this is applicable to both p-type semiconductor as well as n-type semiconductor. Okay, so these are certain equations which is used to know about the type of semiconductor. But I will tell you one more thing, that actually what will happen, that if we know the type of semiconductor, okay, suppose if we take a p-type semiconductor, this if we take p-type semiconductor, then what will happen? This p-type semiconductor has certain force due to magnetic field, which is nothing but the Lorentz force, and we know that Lorentz force is designated as QVB sin theta. Since it is perpendicular, so we are taking sin theta as 1, so it will ultimately be equal to QVB. Okay, Q designated charge, V is voltage, and B is magnetic field. Okay, and since this force will be balanced by current, which is flowing in the exactly opposite direction. So due to electric field. So since we have two types of field, so electric field will balance the magnetic field, and our magnetic and our force due to magnetic field will be QVB, and either we can say the force due to electric field will be Q into E. Okay, so ultimately it will becomes E. E will be equal to V into B. This E will be V into B, because due to Lorentz force is QVB, electric field is Q into E. This Q and Q will get cancelled, and ultimately we will get E is equal to V cross B. Okay. Now we know that V is equal to IR, but here in semiconductors this will be equal to G upon N, where J is the current density. Okay, and this Ne, this is nothing but known as 1 upon NEI. Rather, this is known as Hall coefficient. So this is Hall coefficient, you can see 1 by Ne. Okay, so this E will be equal to J by Ne into B, or we can say that 1 by Ne into JB, and this E is equal to, this is Hall coefficient into JB. So this is how actually we will be able to know about the Hall coefficient. And this, if this Hall coefficient, this is negative, that means we have N-type semiconductor. And if this Hall coefficient is positive, then we will say that it is P-type semiconductor. And for P-type semiconductor, in spite of N, we write P, and for N-type semiconductor, we write it as N. Okay. So this was all about my today's presentation or lecture or the interaction with you. And finally, we have applications of semiconductors. So there are actually whatever the electronic or electric device we have nowadays, right from your cell phones to washing machine to television or any equipment you will take, it has a semiconductor inside it. And there are a number of applications of semiconductors. It can right here it is written like temperature sensors, but it is not limited to temperature sensors only. There are a number of sensors which are made from semiconductor devices. They are used in 3D printing machines. Nowadays 4D printing also possesses these semiconductors. They are also used in microchips and self-driving cars. We all know that if you have a computer, there will be a chip which is made from semiconductor devices. They are used in calculators, solar panels, computers, all electronic devices, transistors, MOSFETs. Actually, the basis is semiconductors. Okay, physical and chemical properties of semiconductor we can change, and by which we can have number of devices. So in short, I can say that semiconductors play central role in the operation of any electronic gadget. Like here it is written bank ATMs, trains, internet, communications, everything I can say. And nowadays you can see that actually as the technology is getting modified, now we have self-driving cars in some cities, also in developed countries. Thank you very much for your kind attention.
Thank you so much, sir, for the knowledgeable presentation. Now I request Ms. Vaishali Sharma to present a vote of thanks.
A very good afternoon to all. Thank you so much, sir, Dr. SANDEEP ARYA, sir, that you shared your precious time for our students. I hope that our students must have received the knowledge given by you. Once again, thank you so much. I'm again thankful to Director Ycet, Dr. Anup Kumar Srivastava, sir, for attending the program. My sincere thanks to Dean Academics and President of IICCL, Dinesh Gupta, sir, HOD Applied Sciences, Dr. Rakesh Verma, sir, and students for attending the session. Once again, I thank you all.
Thank you, ma'am. Thank you, sir.
So is there any question from any student? And I hope actually I have not bored you people.